So to start with, what am I talking about when I refer to a physical climate risk? So I'm just quoting here from the Task Force on Climate-Related Financial Disclosures. So this was a task force set up with the backing of some international financial organisations, and they identified two distinct types of climate-related risk. One they refer to as transition risks, and the other they refer to as physical risks. So these are risks that businesses will face, or are facing currently. So transition risks are really around the idea that in order to address climate change, we're going to have to introduce different policies and different regulations that will impact how a business runs. And that's a risk to how the business will work, and they need to factor that into their future plans. So this might be an introduction of a carbon tax or a carbon market, these kind of things. The second risk they face is these physical climate risks. So businesses own assets. Those assets are vulnerable to various weather extremes or climate hazards, and they need to be aware of those and factor those in to their future plans as well. So they talk about two different types of physical climate risks, which I just summarise here. So probably the dominant type that we can easily imagine that are risks we already deal with today are the risks associated with extreme weather events. Okay, so you can imagine any asset that a business or a government or a community might own can be damaged by different types of extreme weather events. Now, if these extreme weather events are changing in the future, their intensity, their frequency, their location, then those changes are changing the risks associated with those assets. Of course, with climate change, it's not just about these extreme events. We also have some long-term changes that are impacting us as well. The most obvious one is sea level rise. So any of our assets which are at sea level, close to the coast, of course, are going to have to factor in sea level rise over the long term in terms of what the risk is to any assets close to the sea level. But there's also other long-term risks, such as changes in water availability, which has consequences on water quality and water supply. That can be, rather than event-driven, can be long-term changes in these aspects. So when we're thinking about climate risk, we think about these kind of things in the climate system. Now, in the IPCC reports, they've adopted this schematic to talk about risk. And you can see here, they present risk as the intersection of the vulnerability of a given asset, the exposure of that asset to a particular hazard, and of course, the hazard itself and any changes that might be occurring in the hazard. All of these things are influenced both by the climate, but also by many socioeconomic factors as well. So you need to know about all those things if you want to understand risk in its entirety. Now, vulnerability is really about an organisation understanding their assets and what kind of events or long-term changes will impact the operation of that asset. Okay? So that is really about the organisation understanding its own itself. Exposure is really about when those assets are usually in places that are going to be impacted by various hazards. Okay? So if you have a production facility that you build it in a floodplain, well, it's going to be exposed to flooding, whereas the same facility built on higher land further from the river would not be exposed to that hazard. And of course, the hazard itself, which is what I've already mentioned, these physical climate risks. So these are either can be thought of as extreme weather events or these longer term changes that are happening because of climate change. So the vulnerability aspect is really about an individual organisation understanding themselves, so I'm not going to talk too much about vulnerability. I'm now going to focus on these climate hazards and the related exposure. So where the hazards are occurring is telling us something about the likely exposure that we might have given our location of our assets. Okay, so we're interested in various hazards and where they occur and how they might be changing, including the location they occur, how that might change in the future. So what are climate hazards then? I think we all can take our own personal experience. We've all experienced some of these hazards in our lives, and we could come up with a list, right? So we've got hurricanes or typhoons are major hazards in some parts of the world. Thunderstorms. Actually, thunderstorms is a very common hazard in many places. Both of these things can lead to flooding. This could be flash floods, or it could be very large-scale riverine floods. And in very local situations, this can lead to landslides, right? That generally affect fairly small areas, but they can be devastating in those areas when they occur. So these climate hazards, these are all sort of wet climate hazards, but we also have dry and hot climate hazards. So droughts obviously can have a big impact in various aspects of society and our infrastructure. Heat waves can also have big impacts. Bushfires. So I'm from Australia. We've recently had some very extreme impacts from a bushfire season that's completely unprecedented for us. And of course, that has impacted a lot of assets that probably most people didn't factor into any of their plans given that season. And then long-term changes like sea level rise. We've got lots of cities built at sea level on the coast, and a few metres of sea level rise could be a very significant impact and pose a really strong risk on a lot of these assets. So there's a wide variety of these hazards that we face, and depending on where you are, different hazards will be more or less important. Okay, so not all these hazards are that important. If you're not in the tropics, then probably you're not going to be impacted by hurricanes or typhoons, for instance. So you need to look at your location to understand which hazards are the things you really need to pay attention to understand your risks from climate-related events and how that might change in the future. So we can look at Malaysia. Here's from the United Nations Disaster Risk Reduction Organization. This is the frequency of these hazards affecting Malaysia. You can see here that Malaysia's most common hazard is flood. So more than half of the hazards affecting Malaysia are floods. They don't distinguish between flash floods or large-scale riverine floods here, they're all together, but clearly floods, major hazard here in Malaysia. Next we have storms. So thunderstorms are a major frequent hazard in Malaysia. Then we have landslides. Then we have, what do we have here? Wildfire and drought. So of the 7 they list here, the top 5 are all climate-related hazards for Malaysia. So this is in frequency, of course. Just because something occurs often doesn't necessarily mean it's the most important one to look at. You might be interested in other factors such as mortality. So if we look at mortality, we see actually storms have the biggest impact in Malaysia. They don't occur the most frequently, but they cause the most mortality. So if you're interested in saving lives, you would probably want to look at storms and how frequently storms are changing, or what sort of changes you might expect in storms in Malaysia. Of course, floods, landslides, still in there, and they're not unimportant. But you can see it's a slightly different view of things if mortality is your thing of most interest. You can also look at it in terms of economic costs. So what's causing the largest economic costs? So now you see floods again cause the largest economic cost to Malaysia. But then we see slightly different. Next we have earthquake before wildfire. And storms are a much smaller total economic cost. So you can see, depending on what you're most interested in, different hazards will be the hazards of most interest to you, or the hazards that pose the biggest risks to you. Okay. But nevertheless, you can see that climate-related hazards, whichever way you look at it, account for a very large proportion of the hazards that we face as an organisation or society at the moment, and that we should expect will change in some way going forward as the climate changes. So we're aware then that we have all these hazards to these climate-related events and changes. If we want to understand our risks in the future, we need to project how these hazards are changing in the future. So let's just think for a minute about how it is that we project future climate change. Okay? And then we'll try and work towards how much we understand about these hazards and how they're changing. So our main tool for understanding how climate will change in the future are, of course, climate models. And these are a prognostic system of equations that represent the physical and dynamical processes that control climate. So the climate system by its nature is global. So if you want to understand how the climate might change, you need to start from a global perspective. And the way we do that is that we split the globe up into some kind of grid. We have our set of governing equations, which we solve on this grid. We have some forcing conditions. So for climate change, the forcing conditions are the atmospheric composition and changes in the atmospheric composition. This is the main forcing condition. We have to have some initial conditions. So we have to tell our model what the entire state of the atmosphere and ocean is when we start the model run. And then we can run our model forward, and that will give us our model output, which in this case will be the state of the climate at some point in the future. So these are three-dimensional models. So we have, the grid isn't just flat on the Earth. We have a vertical atmospheric layers. We have a similar thing in the ocean. We have vertical depth layers in the ocean. And we're solving all our equations on this three-dimensional grid. Within these particular grids, there's some other things that happen. We have radiation interactions with our atmosphere and our ocean. We have the formation of clouds and rain, various other aspects like this. And so our model has to solve for all this. So our governing equations that the models, the core of the model is based on, are these 5 things. Okay, so our conservation of momentum, which is really the how and why wind changes. We assume a hydrostatic balance in these global models. So this is a function of the density, height, and gravity. Okay. We conserve mass, right? So we don't magically create any atmosphere or lose atmosphere. We conserve energy. We don't create or lose energy, we just change it from one form to another. And we have an equation of state, which is, for the atmosphere, is the ideal gas law, and that relates pressure, density, and temperature of the atmosphere. Okay. So we have this system of partial differential equations that we solve everywhere in our grid of our model. Now, there's a whole bunch of other things that the model has to take account of, which occur at scales smaller than our model grid. So to account for these, we have these sub-grid scale parameterizations in the model, and they have to do things like account for the interaction with the surface and the planetary boundary layer, so the lowest part of the atmosphere, and that allows us to exchange momentum and moisture and heat between the surface and the atmosphere. We have to account for radiation interactions in the atmosphere. Okay, so radiation interactions are occurring at molecular scales, so obviously we don't resolve them explicitly in the model, so we parameterize them. We have to account for convective or cumulus processes, so how we generate these large-scale convection that gives us our cumulus clouds and our major thunderstorms. These happen at scales on the order of maybe a few kilometers, which is much smaller than our global model's grids, so we need to parameterize that. What happens at the land surface? So how we partition our energy between latent energy to evaporate water from the surface as opposed to sensible energy, simply heating the surface. How we move water around through the soils and through the vegetation on the surface. That's all parameterized. And cloud microphysics. So how do we form clouds, right? So these things happen at micrometer scales, the formation of cloud droplets, the lifting of these, the freezing of these into ice crystals, the creation of snow and rain, very small scale processes. So we have to parameterize those in our model as well. So these models have been developed over many decades by large groups of people. These are very complicated models these days. Typical global model might have a million lines of code, something like that. And this just gives you an idea of how these models have developed in complexity over time, where extra processes that are occurring in the climate system have been added into these models over the decades. And the models that we are using today are representing all these different processes in them in a very explicit way. So some explicitly on the grid, some parameterized within as subgrid processes. But there's a limit to this, okay? So if we have to split up our globe into a kind of grid, both horizontally and vertically, then if we want to solve these dynamic equations on the grid, then having smaller boxes obviously means we need a lot more of these boxes to cover the Earth. But it also means that the way we solve the equations, if you have a smaller box, then you have to have a smaller time step to solve the equation. Okay. And that means that to halve the grid size actually increases the compute cost of such a model by something like 8 to 10 times. Okay. So the higher the spatial resolution you put into the models, the more rapidly you increase the compute power required to solve them. Okay. And this rapidly becomes very challenging with today's compute resources. So global models that use about a 50-kilometre grid are possible now, but you need petascale computers to do that. There are petascale computers in the world, but they're measured in the few tens of computers globally. And so at the moment, most of these models are still running at something like 200 kilometres. Some organisations down to 100 kilometres these days in the latest generation. Okay. But you can imagine that at 200 kilometre resolution, there's a lot of important things for the climate system that are missed by these global models. And we can take a look at what the land surface looks like in one of these models. So I'm from Australia, so this is Australia-centric, sorry about that. So here we have Australia in one of these global models. This is the representation of topography that the model sees. And you can see things like New Zealand is just 3 grid points down here. Might be hard to see, but just off the bottom of Australia here is Tasmania. It misses out, it's not actually in the model. You can just make out the Malaysian peninsula here. It's land, but the isthmus is too narrow and isn't land. So the peninsula in this model is not actually connected to the rest of Southeast Asia. So at these low resolutions, you can get some funny things happening in the global models. So that's, if we're really interested in these climate hazards, then that's not ideal. So we need to do something to improve on that, and we can't do it globally because we don't have the resources to solve these things at high resolution globally. So what we can do though is called downscaling. So the idea here is that we want to derive local regional scale climate given information of what's happening outside our region of interest. Okay, so the assumption is that these large scale conditions that the global climate models are able to solve have an influence over what's happening in our local area, and we can take that influence at some boundary around our area of interest, and we can solve over our area of interest at much higher resolution and resolve a lot of these features that are missing in the climate model. So we can think about different scales then and what we might get out of different climate models. Here I've just sort of split our scales up into 4 different sizes. So obviously we start at the global scale. The climate system is global by nature, so we start there. And then we go down to continental scale, regional scale, and city scale. Okay, so if we're really interested in the risk to assets, we probably need to be at city scale for a lot of those questions. If we think about the global climate models then, they're definitely solving the climate system at global scales, and we've got a lot of evidence that they actually, in a global mean sense, do quite a good job. Even at continental scale, when we look at the representation of continental mean climate, the global models do quite a good job. But they're really struggling to get to regional scales, and they're certainly not giving us much information at city scales. So GCMs are good for these large scales, but if we want to get down to these smaller scales, we really need to be using some downscaling techniques. Okay. So one of these techniques is to use regional climate models. Okay. So these are similar to GCMs in a whole bunch of ways. We're integrating the same primitive or governing equations as the global models are. Because they're solving all these equations together, they provide a coherent picture of what's happening in the climate, both in space and time, but also in terms of relationship between all our climate variables. Like the global models, they still need subgrid parameterizations. Okay. And because the regional model is only doing a limited area, for example, here's one example here, it relies on the global model to get large-scale teleconnections to climate modes like the El Nino Southern Oscillation. So for instance here, that tropical Pacific, where El Nino really functions, is outside the area of interest here. And so any interaction or connection to El Nino has to come in through the boundaries of my limited area based on the global climate model. So I'm relying on the global climate model to give me that teleconnection. Of course, they do differ from the global models as well, in some ways as well. So the first is that we solve now, at the regional scale, we solve the compressible non-hydrostatic equations. The global models assume hydrostatic relationship in the atmosphere. At very large scales, the hydrostatic assumption is reasonably valid, but at smaller scales, whenever you have systems like thunderstorms and stuff, they break that hydrostatic assumption. So you need to have a non-hydrostatic solution, which we use in the regional models. Of course, we take information from the GCMs at our boundary, and we integrate the equations just over this limited area, but at much higher resolution than the global models can do. Because we're using much higher resolution, that of course means we have to use a much smaller time step as well than the global models do. So that means we can resolve things in time much more better than the global models, as well as resolving things in space much better. The regional models also tend to include parameterizations we might not have in the global models, because at the global model scale, certain things might not be as important. So one example is the urban environment. At the global scale, with the global models, most of them have very little representation of city landscape, whereas in the regional models, we explicitly have additional parameterization in there to model the interaction of the urban landscape with the climate itself. And this has a really strong effect if you're interested in what might be happening to assets in cities' areas. Various other things we get included, explicitly including lakes in the regional models, various things around orographic drag, fire spread or hydrological models. These are all things we can include in the regional scale models that generally not included in global scale models. Okay, so we've got our climate models. We understand that global models have scale limitation, but we also have the regional models. So when we think about our climate hazards, we can think about how our climate models actually can simulate and represent those hazards. Okay. So I've talked a fair bit about the spatial scales that the climate models can address. So let's think for a second about the spatial scales of our various climate hazards, okay, because they're all different. So tropical cyclones, let's think some can be up to sort of 1,000-kilometre scales across the super typhoons, but we need to get down to 10 kilometres if we want to capture properly the eye of a hurricane and the dynamics. Arguably even less than 10 kilometres to do that. So there's quite a large spatial range we'd want to capture if we want to do tropical cyclones properly. Thunderstorms are much smaller, a few kilometres maybe. That's how big these phenomena are, so that's what we might think about. Riverine floods, they can be quite big, right? They can cover very large areas. and they're not too small, tens of kilometres at least, I would say, whereas flash floods can be much smaller, especially in urban environments. They might be affecting only an order of a kilometre or a few kilometres. Landslides, of course, very local phenomena, probably talking hundreds of metres to kilometres. Droughts tend to be much larger, so they tend to affect fairly large areas, maybe hundreds to 2,000 kilometres. Heat waves, similarly, tend to affect fairly large areas. Wildfires, large variation in wildfires, anything from kilometres to hundreds of kilometres. Although if I take the example of this summer in Australia, I probably should have thousands of kilometres in there. Sea level rise, generally very large scale effect of sea level rise, but it's not uniform around the globe. So there's lots of regional variation in sea level rise as well. So you probably need to get down to the hundreds of kilometres to understand what to expect in your area of interest as well. Okay, so we can think about different scales with the hazards, and then we can try and match that up with the scales that our models, climate models, can do. And you can see from this that there's a few hazards. We might expect some useful information from our global models, but probably better information from our regional models. There's a number of hazards that you could only get useful information from regional models. And then we still have landslides, which kind of right now are even smaller scale than we're able to do with regional models. Okay, so how well do these models actually represent hazards? So let's look at what's been reported in some of the IPCC reports in recent times. So I'm going to start by going back to 2012. That was when they did a special report on extremes, so managing the risk of climate extremes and disasters. And this report back in 2012 relied very much on global climate model results, but they made a number of conclusions. First, generally around temperature extremes, that the model projects substantial warming in temperature extremes, and likely that the frequency of heavy precipitation would increase as well. So generally, an increase in both temperature and precipitation extremes. However, they had low confidence in projections of winds, extreme winds from the global models. Sea level rise was very likely, so there's pretty good confidence around this, sea level rise. And then they looked at floods, but there was fairly low confidence in what they could say about floods at this stage. For droughts, they had medium confidence, but they had medium confidence around droughts. If we come forward, the following year, they had the fifth assessment report. It made some other, so this was again based largely on global climate models, but it was actually the next generation of global climate models than the previous report was largely based on. In this case, they had found medium as high agreement that temperature extremes were represented well by the models, so this new generation was doing that even better. So they had more confidence in the temperature extremes conclusion than they had the year before. Slightly less confidence about the rainfall extremes. So the new generation was doing definitely better with temperature, a bit better with the rainfall. And then when they now have a conclusion around tropical cyclones. So it's likely that the global frequency of tropical cyclones will decrease or remain stable. But a likely increase in the global mean tropical cyclone maximum wind speed and rainfall. So now they have this interesting conclusion where the numbers are likely to go down for tropical cyclones, but you're likely to see an increase in the maximum wind and rainfall, so the intensity going up even though the numbers going down. And then they had this sort of medium confidence statement around aspects of drought, so that was quite similar to the previous report. Now, if we come more recently, so this is a report, special report released last year. I was actually an author on this report. This was known as the report on climate change and land, special report on climate change and land, largely because its official title was rather long and unwieldy. But we now were basing much of our conclusions not just on global models, but on what regional projections are saying. And now you can see we're able to make some conclusions that we're not able to make based on the global climate models. So some reinforce the conclusions we had before. So again, this idea that the high intensity cyclones are expected to escalate. We also, with a focus on processes that cause land degradation, we're able to say a few things here. Increasing in floods, medium confidence, drought frequency and severity, which I mentioned up here, the intense cyclones, and sea level rise with very high confidence. Lastly, this report was the first one that had a conclusion, which I put down here. Future changes in climate and urbanisation will enhance warming in cities and the surroundings, especially during heat waves. So this is the first time we've had a city scale conclusion appear in one of the IPCC reports. So there's enough studies around at scales relevant for cities that we were able to make a conclusion about something to do with heat waves and heat extremes in the cities. Now, there was no equivalent conclusion around changes in rainfall over cities. The evidence for that is much more mixed. But there are examples that we can look at that I think means we will see in the future, as more studies at this scale come out, we will see some conclusions around this. And here's an example for Kuala Lumpur. So here, what you can see here is the urban footprint of Kuala Lumpur from 1989 to nearly the present. So you can see there's been an amazing expansion of the urban footprint of Kuala Lumpur over the last 30 years or so. It's really grown dramatically. And you can see the red and blue dots in here are different meteorological stations. Some of them are in the urban footprint, some are in the surrounding countryside. If you look at the change in the intensity of the most intense events, the top 5% intense events, for the urban stations at the top and for the rural stations at the bottom, you can see there's been quite a dramatic increase in the intensity of the most intense events inside the urban area compared to the rural area, which has seen almost no change over this time. Okay. So here's an example where the changing urban footprint is having quite a strong impact on the rainfall hazard experienced within the city. Okay. So we saw before, we already see this effect in temperature extremes and heat waves, and in some places like Kuala Lumpur, and I think this is probably generally true for major cities in the tropics. We see similarly large impacts on rainfall extremes in the urban area as well. Okay, so that's my summary of the IPCC and what they've said. Here's now my completely subjective assessment of how well we can do each of these hazards based on what previous assessments have said and more recent work. And so here's what I'm suggesting where we currently are at. So there's a few of these hazards around sea level rise and heat waves that actually we do really quite well, and we can use our current projections to assess changes in risks in these hazards. There's a bunch of other ones that we do okay. There's useful information there. We can do something about assessing risk based on those hazards, but we still need to improve what we do with our models in terms of those hazards. But we're left with a few hazards that we really can't say much about based on the current generation of climate models and climate projections. And that's around thunderstorms, flash floods, and landslide. Now, if we recall our hazards in Malaysia, that group of three, thunderstorms, flash floods, landslides, is a large part of this frequency wheel of hazards, climate hazards in Malaysia. So while there's a bunch of hazards that we already have information we can use to assess risk, unfortunately there remains a number of hazards which in many places are the major dominant climate hazards that we currently can't say much with confidence about their future change. And that's a problem for assessing climate risk going forward. So what do we need then to actually simulate these changes in these climate risks? Okay, so it's really, we need a whole bunch of things to happen. Of course, there's an overall improvement in numerics and the core parameterizations in these models. This kind of work has been ongoing for a long time and continues. But we really need to get down to these kilometre scale resolutions to start addressing these important hazards that are mostly missing from our current projections. There's some advantages to getting to this scale, which I won't go into. We need to have improved urban hydrology representation. So we've seen in the observations that the urban landscape can strongly impact the local climate, and that's important to capture in the models. So we need to do that. In order to do this, we really need to be evaluating our models based on how they represent these hazards. Most of the development to date has really been about improving the way the models represent mean climate, seasonal climate, but we really need to be looking directly at these hazards. And that, of course, means we need observational data sets at the right scales in time and space that allow us to do that kind of assessment, a hazard-based assessment. So, what should we be doing? We should be doing these kilometre scale models, but to do this right, we need to do it over large areas, right? So if we want to capture some of these large scale climate hazards, we need to be covering thousands of kilometres at this kilometre scale resolution. We need to do it for long durations, right? So we're talking about the length of lifetime of assets is what we need to do. And some of these assets might be 50, 100-year lifetimes, so these are the scales we need to model. We need to do multiple emission scenarios, right? So to understand this trade-off between transition and physical risk, right? If you want to mitigate quickly, you can make your physical risk, keep your physical risk low, but that means your transition risk is high in the short term. And you've got this, and vice versa. There's sort of a trade-off in risks here. And you need to do it with multiple climate models, and that's largely because there's a lot of uncertainty in the structural components and parameterizations in these models. So we need to sample that uncertainty in order to have robust future projections. To do that, though, we'll require multi-petascale compute and data storage. So currently, there's probably a handful of places in the world that are capable of doing this right now. Over the next 5 to 10 years, though, I expect this capability to become much more widespread. And this is where we should be aiming for in order to properly understand climate risks going forward. So, my summary. Future climate change will alter the characteristics of climate hazards. Okay? It's not just about the change in global mean temperature, it's really about what that mean change means for these extreme events. Okay? We have some information already that we should be using, but we need improvements to cover all the climate hazards. So most important climate hazards vary by region, so you need to understand your region to understand which hazards you need to be looking closely at. In Malaysia, that's floods, thunderstorms and landslides, followed by wildfire and drought. The climate model ability to represent these hazards varies quite a lot by hazard, so you need to be paying careful attention to that, because we have high confidence around sea level rise and heat waves, but relatively low confidence around thunderstorms, flash floods and landslides currently. The good news is that climate models do continue to improve their ability to simulate these hazards. And I'd say in the last 5 years, there's been quite dramatic improvements. And I expect we need a step change in resolution and capability going forward. I think the next 5 to 10 years, we'll see such a step change in our capabilities. Later today, you'll hear from Professor Tanang, who's going to present some results from some regional climate projections for Southeast Asia, which is heading towards this direction. With that, I'll end. Thank you.